Hey guys, it's Simon and welcome back to my LibGDX Kotlin tutorial series. In the last part we learned a little bit about the movement, damage system and how to use these different systems and also how to debug our game with the debug system. And now we are going to fix a small thing, which is the time step of our game. And I will link a very good article in the comments below. You can read about that, what that is and why you should care about that in your game. And I will show you in this part how you, at least there's one way, how you can solve the problem. To describe the problem, let's assume this would be our game screen, so like this. And let's say there is a player moving from the left to the right, and this would be one time step, so one frame. It jumps from the previous frame to the current frame. It would jump exactly this distance. So if we would have here now a player, let's make a small rectangle. So at the time 0 of our game, the player would be here. At the time 1, he would be here. Time 2 would be here, and so on. And also imagine that this is zoomed in very largely. So usually he would actually jump just 1 pixel, let's say, between 2 frames. And this is just a representation, a very highly zoomed in representation of our game, let's say. And the problem now is, so if our game would run with a constant frame rate, so let's say 60 times per second, then the player would fluently always jump and very smoothly jump exactly one distance here. And to our human eye, it looks then like a smooth movement if he always moves the same distance between frames. But the problem is that computers and any devices actually where we run our game will never run at the constant frame rate. So that's why we will have the issue that sometimes he will jump 1 unit, sometimes he will jump maybe 2 units, and then it does not look smooth to the eye. It looks like a little bit of a lag, let's say, or not a very smooth movement. And we can fix that with 2 things that we apply to our game. So one thing is that we solve, which is actually a different problem, the so-called spiral of death. So let's imagine our scene that we are drawing is very time consuming and the device cannot handle it. So it maybe goes down from 60 frames per second to 30, 20, 10, 5, and it cannot keep up with our game logic. So the game logic, 1 frame takes more time than the computer takes to process it. So it goes then down until we are really stuck because it cannot render even 1 frame within the given time. And then it looks like a stuck picture, and most likely at some point the game will crash. And this is one problem. It's called the spiral of death, and we will just fix that very easily by defining a minimum amount of frames per second that we are going to support. If it drops below that, we will still update our entire game logic with that amount, so we cannot go below that amount to avoid that. And the second thing is that we are going to introduce an interpolation. So in case, let's say again, the player would not jump exactly one distance between a frame, he would jump maybe 2 because the delta time between 2 frames was too big. Then we will not jump immediately to this position. We will actually smooth the rendering. So we will slowly go to here. So it's a so-called interpolation between the different frames. And this is also what we are going to look into that today. So as mentioned, the first thing that we are going to fix is in our game screen. So there we're going to define now a minimum amount of frames per second, or delta time, let's say, that we are going to support. So if we drop below that, we will still use that value for the delta time. So it's actually a maximum amount. And let's say we don't go below 20 frames per second. And now the only thing that we need to change is in our render method of the game, where we pass in the delta time to our engine, which could currently be anything, could be 5,000, so could be, I don't know, only half a frame, could be 200 frames per second, so a very small time or a very big time. So we are going to fix that by defining now here, by using now our maximum delta time for our update logic. So what we're going to use here is the minimum amount, We can use again the Kotlin minimum for that. And the minimum is either our maximum amount of the delta time or the delta that we get passed in from LibGDX. So now, if our minimum amount of frames per second would be 20, if we run faster like that, so 60 frames per second, 40 frames per second, then delta will be passed in, so that the lower amount of that. And if we go below, so if we have a higher number, so only, let's say, 2 frames per second or only 1 frame per second, then actually this number will be used for our update logic, so 20 frames per second. So we will not get stuck to avoid the spiral of death. You can read about that in the article that I mentioned in the comments below. So this is one fix that we should apply. The second thing is that our move system needs to be updated as well. So a certain logic in our game, especially when it comes to the movement here, the rendering should use now the mentioned interpolation that I mentioned. And to make that happen, so to go again here to this graphic, so make it happen that the player does not jump immediately here or does not immediately jump there. We want to smooth it, so we want to interpolate between those frames. And to make that happen, we need to adjust now our transform component, which currently just have a position, and we update it. So currently we would do this. So update it, bam, go there, or update it, bam, go there. And to make now the smooth transition, we need to remember the position before we update the movement. We need to know the position after the update, which could be there. And we need to know how which amount of percentage are we between 2 frames. So if we are exactly at the new frame or at the old frame, we would render here. If we are exactly at the new frame, we would render here. And if we would here somewhere in between, because we don't have the exact amount of frames per second that we define for our update logic, then we would smoothly transition, interpolate between this range here. So let's say, again, maybe we are at 50% between a full frame, so we would render it here. If we are 25% until the new frame, we would be here. If we are 90% at the new frame, we would be here. And with this percentage between 0 and 1, we come to that in a moment, we can now define where we want to render our player. And we can, if we don't have exactly always, if we don't, with our delta time, if we don't hit exactly one update frame all the time, then we will now smoothly transition between those. Okay, so as mentioned, so first of all, we need to update our transform component. So what we need now as well is the previous position before we update something. And we also need the interpolated position that we use then later on for the rendering. And we also need to reset them correctly. And when we spawn a new entity, instead of setting then the position, previous position, and interpolated position, because actually we need to set all 3 of them to immediately move an entity to a specific position. Also from the rendering point of view, we define now here a helper function. Let's call it set initial position. And now we're gonna simply update all our 3 vectors to these values. Okay, so the next thing we want to do before we go to our move system and fix it, instead of calling here now position set, we use now our helper method, so set initial position. Okay, and the next thing is now in our move system. So there we add now the interpolation part. And what we are now doing, so before we update our entities, so before we move to the new position, we need to remember what is their position before we update them. So for all of our entities, so before we're gonna update, we get the transform component of each entity. And here we use the let syntax of Kotlin. So if it would not have a transform component, which could actually never happen, because we only iterate over entities with a transform component. But again, we could use here the require part, but in this case, I like to prefer here the let syntax. So we have here our transform component, and of our transform component, we want to save the previous position, which is actually the current position of our entity. So here we store the current position of our entity in the previous position, and then we're gonna update it to the new position. Coming back to our graphic, so this would be the previous position. We remembered that. Then we call our update logic, which could be that the player jumps here. So this is the previous position, this is the actual position. And now we want to interpolate between those two positions, so between the previous and the real one. And this is then actually the position that we use for the rendering to get a smooth movement and to avoid then stuttering in our game. So what we need, they call it an alpha in the article, so we will stick to that. And we just take our accumulator, which stores the time between two frames, or actually our total amount of time which happened since the last update call, or several update calls, and we divide it by our constant update rate. And with that, so since here we already iterate over the accumulator, if it's greater than our fixed time step, then we reduce it. So at the accumulator after this while loop is actually smaller than the update rate, could be 0, but could be very close to the update rate. And with this division, we get the value between 0 and 1, which is actually the percentage between, so how much we are until the next frame. So if it's 0%, then we exactly updated one frame and there is no time left. Or could be also 0.99. Then we are very close to the next frame. And actually with the next update call, most likely we update then to the next frame. So here again, alpha value between 0 and 1. And now we make the interpolation happening. We are now updating the interpolated position. And what we do, so we interpolate between it, and there is a so-called lerp function. Is it called lerp? I don't know how to pronounce it. So this one, linear interpolation between from value and to value on progress position. So from value in our case would be the previous position, to value would be the normal position, and progress is our alpha value, so the value between 0 and 1. So transform previous position x, transform position x and alpha. Same for the y coordinate. And for the z coordinate, we don't need to interpolate because we only used it for the layering of the rendering. So on which am I in the foreground or in the background, and we don't need an interpolation for that. So there we just use the actual c value or z value of the position, and that's it. Okay, and the last thing that we need to do now is just to use our interpolated position. So when we go to our render system, instead of using here position, we use now the interpolated position. And that's already it. So if we run now our game, we will see the exact same thing as we did before, but I can already tell you that the movement already looks now a lot smoother than it did before, because when I record, I can actually not hit 60 frames per second or whatever we defined for the update rate. So that's why it was a little bit stuttering. And now with the interpolation, it looks now a lot smoother already. Should be the same for you. So when you apply this fix to your game, you should also have then a lot smoother movements and rendering than in your game. So it looks a lot better now. So that's the small thing to fix your timestamp. Timestep, again, as mentioned, I will link the article in the comments below to read more about it. But those are the two things that we applied now to fix it. So first of all, to avoid the spiral of death, we define just a minimum amount of frames per second that we are going to support. If we drop below that, we just update still with this frame rate so that we don't get to a frozen picture at one point, let's say. And the second thing is the interpolation that we now updated in our move system. So there, before we really update the movement, we store the position of all of our entities. And after the update, we check how many or what is the percentage between the current frame and the next frame. and we're gonna interpolate then the position accordingly to not jump always a different distance from a rendering point of view, and instead of smoothly interpolate between the real positions of our entities between an update call. Okay, that's it. That's a small part. Thanks for watching. Hope you enjoyed it. Leave me a comment and see you in the next part. Bye bye.